All right, so the purpose of this video is to talk about the stuff you see on the board behind me here. What does AC current look like? Hold on a sec. So what does AC current look like, and what are some definitions, units, things like that, basics? And then I want to explore how these four circuits respond to an AC source. Notice this has a little sine wave in it. I'll zoom in on these in just a minute. So we're going to be curious to see how these AC circuits respond. Notice that's not a battery, it's a new symbol. It's a circle with a sine wave in it. But first, let's understand, oops, come on. There we go. Let's understand the basics here. So the equation that governs an AC source, that will basically, we get a sine wave equation. So let's look at it. There's going to be a source voltage that's a function of time. Okay, AC meaning alternating current. Alternating for AC. So what happens here is we get something that's got some amplitude times a sine function or a cosine, but generally speaking, we're going to use sine. All right. Now already we can see we've got some terms in here. So to be clear, sometimes you'll see me write V source max sometimes I'll write source voltage amplitude, and the units are volts. Well, in this case, just for clarity, I'll write out the word volts. That's the units. Okay. Omega is often called frequency. Strictly speaking, I guess we should call it angular frequency. To distinguish it from F, which is just frequency. Now, I want to be clear here. Every once in a while, I'm going to say frequency, but mean omega, or more on that in just a second. They're related. This one has units of radians per second. This one has units of hertz, or 1 over seconds, or seconds to the minus 1. These two are related by the equation omega equals 2 pi f, the same one that we used in chapter 10, rotation. All right. Now, related to that as well, I might as well go all nuts here while we're doing it. There's a term called the period. And that has units of seconds. And maybe you recall that the period is equal to 1 over the frequency. Or maybe you remember that omega equals 2 pi over the period. There's some different equations. You probably have those memorized by now. You've seen them in a number of different applications. If not, you should memorize them. Just they appear in a number of branches of science. So just have those memorized. Now, let's try and look at this plot and see what it looks like, right? Well, you kind of know what a sine wave looks like. My apologies if it's not perfect here. All right. How do these definitions relate to this picture? Well, on this axis, we're plotting voltage. All right. And I guess strictly speaking, we might be doing delta voltage, but let's just stick to V for right now. Just one less thing. All right. This value right here would be V0. It's the amplitude. So notice the amplitude is the size of the crest. Now, period would be the time between crests. It's the time from crest to crest or trough to trough. Where it gets tricky here is it's not the time from axis crossing to axis crossing. I don't know if you can tell, but that's only half a period. So if you wanted to get the period, right, that would be this time, or this time. So that's, to be clear, the period. It's the time to complete one full cycle, not a half cycle. This is not a period, this is. All right, so notice this sine wave plot here. That might give you some indication of why on the other side of the board, oops, I was indicating an AC source as a circle with a sine wave inside it. All right, now, oops, let's go back to here. Oh my gosh. All right. So we've got our basic definitions and units. We've got our equation. We kind of know what this looks like. Now what I want to do is, instead of doing a bunch of math with this, we're going to do that later. Right now, I want to try and understand what these things are actually going to look like in circuits. So let's go over to some demos and look at them. And I'll try and walk you through a bunch of different demos. All right. So here I've got, to understand AC power, I'm actually going to start with DC, direct current. And I had a couple of cables somewhere. Where did I put them? Ah. Oh, there they are. Give me a sec. All right. So here I've got a circuit. I taped over the breadboard just so things show up better in Zoom. And what we've got, this is a light emitting diode, and this is a light emitting diode. And what happens is these will light up if you pass current through them. And what I did is I wired them in different directions. And let's just take a look at what happens. This is just a resistor here. So again, we just have these things connected with the breadboard. I hope you can see that this light is lighting up. It looks like that's showing up. So now what's going to happen? What if I flip the polarity? I'm going to connect them the opposite way, making sure there's no short circuit. And now this one lights up, and hopefully you can see that. It might not be the same intensity here. Oops, let's get this out of the way there. There you go. So you can see this one's lighting up. And to be clear, you can see it's definitely, when I disconnect, it turns off. All right, so what this means is we can use this light, these two LEDs, to tell which direction current is flowing. All right, so in this case, and before I go past that, I want to also show you this too. I've got this DC motor, all right, and so I just put this paper clip on there and some tape. Let's see what happens when I plug in this DC motor to some power. We see that when I connect the current in one direction, it flows this way, it rotates that way. All right. Here we go. And when I flip the polarity, the flag rotates the other way. Oops, which way? Oh, sorry, there we go. Okay. So depending which way you connect these things, we see two different ways to understand this. We can see that these lights will indicate the direction of current flow or the direction this motor turns. All right, so now let's get rid of this power supply. Second. And bring in function generator. Hopefully that's on the screen. All right, so what this is going to do, notice this has a frequency button here. I can adjust the frequency a little bit. And it also has an output. In terms of the variables that we were just discussing, this is adjusting F, not omega, and this adjusts V naught. So basically, this is like the volume knob or the amplitude, and this is the frequency or pitch, if that helps. So now what I'm going to do is I'm going to attach this thing onto here. and get out of the way. And hopefully you can see it if I crank this all the way up. Yeah, now I can see it. So we see that these lights, and if I slow this down some, we see that the current is going back and forth, back and forth. And if I wanted to see this in terms of the motor, I could just connect this to the motor. Oops. So the idea there is you can see this oscillating back and forth. So I'm just trying to prove to you that we have some sort of oscillation in the voltage, all right? Now, in this case, let's go back to this one. Turns out these physical demonstrations, rapid, and this cable's fallen out, so I'm just going to connect to here. Again, the black tape was just so the lights would show up in Zoom. There we go. Okay, so we've got an extremely low frequency here, right? Less than 1 time per second. And I'm going to speed this up just a little bit. That's maybe slightly over 1 time per second. To be clear, this counter right here takes a while to respond. The number, I don't know if you noticed that. It doesn't respond right away. It takes several seconds to actually get the timing right. But now what I'm going to do is I'm going to try and gradually speed this up. And I'm going to scoot this as far forward as I can just so you can get as good a view as possible. Okay, I'm going to spread these out a little bit. Watch what happens as I increase the frequency. We see it blinking more rapidly now, right? And now what I'm going to do is I'm actually going to go, I can explain how this works later, but I'm going to dramatically increase the frequency by pressing these buttons. The idea here is this button goes up to 5 hertz. This one goes up to 50. So basically I'm changing the decade, so to speak. So this should be 10 times faster right here. All right. And now if I just crank this up, I don't know if you could tell, you don't really see it blinking anymore, right? If I slow it way down, you might be able to see it blinking again. Back and forth, kind of about that fast. But the idea here is if you go faster than your eye can respond, it just looks like both lights are on. We know it's still alternating back and forth. And so this leads us to believe these lights in this motor are not going to be the best way to understand this. Maybe if there's some device that could make a plot of the voltage as a function of time. Well, that's what this is. Let me make sure I don't screw up my cables here. That's what this device is, an oscilloscope. Okay, it's showing up on screen. Now, you can't really read all the dial settings here, but again, we're just trying to get an idea of what's going on. So I want you to think of an oscilloscope as a voltage measuring tool, just like a DMM. And what we could do is we can put one lead here and one lead there. And hopefully I can see this. Did I lose something here? Oops. Where are we going here? Maybe let's hit auto range. There we go. Ah! Okay, and we see this kind of weird looking waveform, right? And this weird looking waveform is in part because of these diodes. So what I might do at this point is, because these diodes aren't really helping us that much anymore, I'm going to go ahead and pull these out of here. And because this resistor is so small, I had to use a very small resistor to make this dramatic. I'm actually going to switch breadboards now. Oops. To this one. All right. And just to show you that it's the same kind of thing, no tricks up my sleeve here before we go too far ahead. All right. We can see it's the same kind of scenario. And again, what I wanted to do is I wanted to switch to this smaller resistor. Actually, this is a much larger resistor, excuse me. Oops. Generally, we try to put black down here. Now, I should be clear here. Black and red don't really matter that much for a function generator. Why? Because it's going plus, minus, and flipping back and forth. But I don't want to explain grounding right now. We'll do that in lab. So for now, let's just say I want to do it this way. All right. And now we can see something on the screen right here. All right.
And if I hit this button auto range, all right, it'll just take a second to respond. And maybe I'll just manually range here. Now you can see there's a sine wave here. All right. And what I'm going to do is gently adjust the frequency. And notice when I lower the frequency, we see fewer waves on a screen. When I increase the frequency, you start to see a bunch of waves on the screen. And then watch what happens here. I'm going to go up a decade. We see so many on the screen, you can't make them out. So let me drop this back down. So what happens now is right now I'm at about 50. And as I increase this, you see so many sine waves at some point, it just looks like a blur and you can't really tell what's going on anymore. So one of the things that's tricky about trying to understand circuits with an oscilloscope versus just with the lights is you're constantly having to think about what the time axis means. We can discuss this more in lab, but you may see me messing around with buttons here like this auto range during this demonstration. And what that does is it's adjusting the horizontal increment scale so that you can actually see the plot instead of getting all bunched up like that. All right, so right now what I want to do is actually add in another connection. Oh, and let me see where we're at now. All right, let's take a look at what we've discussed. Okay, we've talked about what the equation is and what it looks like. We've talked about these units and we've seen real life examples of them doing this, and we're seeing a sine wave. We see that this is actually the circuit that we are discussing right now. Where do we want to go with this? Come on. There we go. What I want to do now is I want to see how these different types of circuits respond when we put this AC volts on it. So all we've done right now is understand, yes, there is a thing such as a sine wave source. We know it has an amplitude, and we know there's some kind of period or frequency or angular frequency omega. So right now, let's start with this circuit and see how it responds. Let's go back. Okay. All right. So if we want to see how this responds, I'm just going to go ahead and do this. Well, in this case, there's not much excitement here. All right. No, we don't even need that right now. So interestingly enough, right, normally when you connect a DMM, you have to clip both leads on here like this, right? But since this is a DMM with more than one voltage reading tool, this is common to both measurements. I only have to clip it once. This is the ground for both of these because ground is common. All right, so now in this case, I'm going to turn on this, and shocking, there's nothing exciting going on. But this is going to be important later. So please just trust me for a minute and just give me some latitude. In this case, well, you can see the two waves on the screen have exactly the same size. And I'm just going to scroll them down here. I'm not changing the voltage as I move these, right? This does not change the voltage, it reads it. And the dials that I'm turning are just changing where it's displayed on the screen. I'm just changing the location of it, not the actual numbers. All right, and what I want to do though here, I can actually change the time axis manually. Oops, let's go the other way. And I don't know if you could see this, but the yellow is the voltage across the function generator, and the blue is the voltage across the resistor. And since they're the only things in the circuit, G, they peak at the same time. I see the voltage across the resistor reaches its maximum at exactly the same time as the voltage across the function generator. And I notice that this is true. I'm going to change the frequency now. If I go to different frequencies, oh, let me change the time axis. Let me hit auto range here. All right. So now what I'm going to do is if I go to a lower frequency, oops, oh, sorry. Give me a sec. I'm taking auto range off now. As I go to a lower frequency, we see they still peak at the same time. As I go to a higher frequency, they're peaking at exactly the same time. This is not that exciting. So what have we discovered here? Let's write up our comments on the board so we don't get lost. What did we discover?
voltage across the resistor is max when voltage across the source is max. Nothing exciting. What we would say is delta VR in phase with delta V source. All right. The voltage across the resistor is in phase. But wait, there's more, Batman. You probably know you could take the voltage across a resistor and divide by R. Well, voltage across the resistor divided by R is current. And just to reduce the amount of writing I'm going to have to do, if I want to fit all this stuff in here, it's going to get painful to write source all the time. So I'm going to switch back to my notation of V0. And so these are all saying the same thing. The voltage across the resistor hit its maximum when the source did. That's the same thing as saying the voltage across the resistor is in phase with the source, which is the same as, once dividing by R, current is in phase with V naught. All right. And so to kind of show this, let's write this. And to do this, what we could do is draw myself a little plot here as a function of time. And what I see is this is the voltage across the source, right? I should be careful here. I should still call this V source. V naught is the amplitude, right? So that's a bad. I should still call this V source. V source was the function of time. V naught was just the amplitude. So I apologize there. But the idea here is the current is peaking at exactly the same time. All right. So this lower curve is current. To be clear, this is a function of time, and this current was also a function of time, right? It was going forwards, then backwards. So positive polarity, you get forwards current. Negative polarity, you get backwards current. All right. Now, I spent some time on this, not because it's difficult, but because this sets us up for understanding the rest of these circuits. All right. All right. So now, oops, let me see if I can still see. Okay, hopefully we're still streaming there. Let's go back to our demo. Now what I want to do is I want to throw an inductor in here, right? And so now we actually are going to have something a little bit more interesting going on. So let me do this. Let me move this down here. All right. Now, if you recall an inductor, let me just show you a big one. Oops. Here's an inductor, actually. It's a giant coil of wire with some iron in it, right? And we could actually connect to these two terminals right here. Whoops, where am I? We could actually connect to the plus and the minus terminal here of this, right? With this plug-in. However, that's impractical. So what we're going to use is this smaller inductor. So this has an inductance of about 70 millihenries. This one, I believe, was about 10 millihenries. So let's get this out of here. So just putting these things in series for right now. And then what I'm going to do is I'm going to first apply the voltage and then measure stuff. Okay, so what I could do is now these might actually be different measurements. This one is going across the entire circuit. So the yellow thing on your screen, let me auto range really quick.
Go. And actually, let's go up to 5 kilo and then auto range. Sorry. All right. Oh, one more. Sorry. So this yellow curve is going to represent the entire voltage across both circuit elements, which is the same as the function generator. All right. So it's the AC source. This is the voltage of the source. Now I've got this other connection. What I'm going to do here is just measure the voltage across the resistor. Right? And so in this case, let me get these both on screen here. Now we're seeing the curves are not exactly the same size. They might not even line up that perfectly if we look carefully. Just a minute on that. But I do want to point out, remember, the voltage across the resistor, if you divide that by R, it's the current. So I want you thinking of the yellow curve or the upper curve as the source voltage as a function of time. The lower curve is the current as a function of time. So now what's going to happen here as I change the frequency, right? Or actually, let's do this. I'm not changing these voltages. I'm just changing where they're displayed, right? Here I'm just changing the units, but I want to point out they no longer peak at the same time. In fact, I see that the yellow curve or the upper curve is peaking before the lower curve. So that means the voltage is peaking before the current. We would say the voltage leads the current, or you could also say the current lags the voltage. All right. So in this case, let's write that down. All right. So we see in this case, how about I say I, what was it here? What did we say it was? So I is lagging. Now I'm going to get a little bit spicy here. Even though this is not a battery, sometimes people think of this as E, like the EMF, right? So sometimes people might say I lags E. I know it seems crazy, just trust me, there's a reason for doing this. The other thing you could say is E leads I. Now in this case, the reason I'm changing these letters like this is because you could see for an inductor, L for an inductor, E leads I. Eli is going to be a way we're going to remember that. Now, in terms of what the plot looks like, let's just draw that plot really quick. Right? So what did we see? We saw the voltage was peaking, and then the current would peak a little bit later. Current was lagging it, right? And oh, they're not necessarily the same size either, right? Sorry, it's kind of hard for me to draw these, but the idea is something like that. All right. All right. One more thing I want you to learn about this. Let's see what happens when we crank up the frequency. So what I'm going to do is I'm going to start dramatically increasing the frequency by multiples of 10. And I want you, I've turned off auto range. So there's going to be some blobs on the screen, and let me actually lower this one down. So again, the upper yellow curve is voltage across the source. The lower curve is current. So this is like E or V, and this is like I. All right. And again, we'd have to divide this by resistance, but whatever. As I increase, whoa, look at that. Look at how small that curve got. Watch this. Whoa. And now if I could, we could just change the time. Oops, wrong way. right? Ooh, too much. There's still a curve here. There's still source voltage. We're still getting an AC current applied, AC voltage applied, but we can see here, it's almost like noise. If I crank up the size scale, it's there. Whoops. It's just so small, even when you blow it up really big, you can barely see it. So what we see, another thing that's interesting is at high frequencies, the inductor doesn't allow current to pass. What if we go to really low frequencies? Well, if I start lowering this down, now I'm going to auto range just so you can see it. Here we go. As I start going down, you can start to see that current growing. And let me get these two at the same scale now. That looks about right. As I get lower and lower, notice the inductor doesn't matter at all. And let's go a little bit shorter here. All right. So at extremely low frequencies, we get lots of current. At extremely high frequencies, whoops. At extremely high frequencies, we get basically no current. That's the other thing I wanted to show you. All right, I apologize if this is a slow video. You can always play back at double speed, I guess. All right. So we see, we're back up here. I equals 0 at high frequencies. I equals big at low frequencies. Now let's think about this quickly. Think, what does an inductor do? It's a coil of wire. It opposes changes in magnetic flux. Okay, well, if you have the current changing rapidly, that solenoid, it's trying to change so rapidly that it has a huge back EMF, or it opposes the change so much that this basically has a huge voltage across it and clamps down on the current. Okay, and so the resistance will have almost no voltage because this is right, when you're changing things rapidly, you get a massive voltage, you get a massive EMF, and then you get no current. The other way, if current's changing very slowly, well, this is basically just a coil of wire. It's got almost no resistance at all, and almost all the voltage will be here. So this makes sense. All right. And now that we're here, to reduce a little time going back and forth, let's make our predictions for what should happen with the capacitance. Well, let's do the same kind of logic that we just did here. If you have a high frequency or a low frequency, what's going to happen to the capacitor? If we have a low frequency, the capacitor is going to charge up and block the current. So at low frequencies, the capacitance has no current. At high frequencies, I equals a big number. We expect the exact opposite kind of thing should happen. Inductors block current at low frequencies. Capacitors block current at high frequencies. Oh, wait, what did I say? I don't know what I just said. I'm going to say it again. I'm tired. Inductors block current at high frequencies. Capacitors block current at low frequencies, right? High frequencies, it opposes the EMF. Low frequencies, this gets charged up. All right. Well, take a guess. These are going to flip-flop as well, right? So you might guess you get ice. Said another way, I leads, whoops. E. So if we had to plot this, we might expect a plot that looks like this. Well, I is going to peak first. Well, actually, let me do this. We still have our source sine wave. But now what's happening is current is peaking a little bit before.
like that. All right, that's what we expect. Let's go take a look and see if I'm lying. Okay, so now what I'm going to do is I'm going to pull this inductor out of here. Oops. And I had a capacitor somewhere. Okay, we've got our little capacitor here. Come on. Go. All right, I'm going to apply my voltage. I'm going to measure the yellow upper curve is measuring the voltage across the source. Make sure these are all well seated. All right. And then let's go down here to somewhere in the middle. Let's hit auto wrench here. All right, and maybe we'll go to a lower one. Let's see what happened. Oh, that's right. There's, sorry. Okay, this actually makes sense. At low frequencies, right, the capacitor charges up and blocks the current. So if we go to really high frequencies, we start to see more current. If we go to really high frequencies, we see a lot. Now, actually, let's look at the peak. Let's see which one peaks first. So I'm going to change this just to make it a little bit easier to see. Whoops, other way. Right, and now I'm going to line these up. Look at that. As expected, we see the current is peaking before the source voltage. All right, so this is looking good. Well, now we have to predict. So now let's go back and review. Sorry, keep going back and forth on you. It's a tough section, so I apologize if this video is too long for you. In this case, we've discussed these three circuits. Now we're going to try and put an L, a C, and an R together with an AC source, not a battery, an AC source. So we're trying to figure out what happens in this scenario. Well, now we're going to get to some different things, and I need to clarify what I'm plotting on each of these axes. All right. So to be clear, this was voltage versus time, right? And this is voltage versus time. And again, even though I'm showing current, right, the current is essentially voltage across the resistor. So these are all voltages versus time. Voltages versus time. All right. What happens if we put them all three together? All right. If you try to put all three of them together, well, let's think. We know what the inductor does, right? At high frequencies, the current goes to zero. We know what the capacitor does. At low frequencies, current goes to zero. So this is going to be tricky. Furthermore, there's going to be, it's not clear which thing will lead. It turns out in this case, depending on what frequency you use, one of these circuit elements will dominate. So we see in this case, right, at low frequencies, the capacitor is shutting down current flow. It's dominating the circuit. So at low frequencies, it's capacitively dominated. We're going to use ice. Current will lead voltage when the circuit is capacitively dominated. And then at high frequencies, the inductor dominates. At high frequencies, we expect Eli. So if we're at very high frequencies, the voltage, source voltage, will peak before the current flow. And then even crazier, this begs the question, there must be some frequency that's just right where these two have equal power, right? Or equal dominance, I should say. And that frequency comes it turns out, we'll discuss how this comes about later. At this special frequency, omega naught, this is sometimes called resonance. Okay, resonance omega naught. To be clear, this is not omega. Omega is the frequency of the function generator. Omega naught is the special frequency where the capacitance and the inductance have equal merit in the circuit or something like that. Sorry, I'm misspeaking. All right. Now, in this case, maybe we should actually take a look at what this looks like. So now what I'm going to do is go back to here. Okay, can we still see this? All right, and so just so you can see, the circuit's getting kind of messy here. Now what I've got is a resistor, a capacitor, and an inductor. And I'm going to show you a demo in just a simulation in just a second. Okay, so we've got a resistor, a capacitor, and an inductor. And in this case, we can see what happens here. I've done the math for these particular circuit elements. The capacitance is about 10 nanofarads. I think it's 11 nanofarads. The inductance is also 11 millihenries. So we've got 11 nanofarads for the capacitance, 11 millihenries right there. I don't know if that'll show up, but that's what we've got. All right, for the inductance. So now in this case, what do we see on the screen? Well, maybe this time I might actually put back in, well, no, let's do this. All right, what I'm going to do is I'm going to start at low frequencies in auto range. So keep in mind, the time scale is going to keep screwing up on the screen. Don't worry about the number of waves per screen. That's going to keep changing on us because of the auto ranging. All we care about now is the relative size of the blue curve and the yellow curve, or the top curve and the bottom curve. What we see right now is at extremely low frequency of 4 Hertz, I see big source voltage and no current. As I go upwards, still not much. Now I'm up at about, now I'm at 1,000 Hertz. We still don't see much, or wait, no, I'm at 300 Hertz. Now let's go 3 kilohertz. I'm going to auto range so I can see this. We're starting to see some current flow, and watch this. Oh, I think it's the next decade. I apologize. All right, so now we can finally start to see some current flow in here. We're now at 4 kilohertz, and watch, as I ramp this up, the current's starting to spike up. I'm going to take off the auto range for a second. Whoa. You see that? Whoa. All right, in this case, I'm going to line these up again. I see there's some special value where the capacitance and inductance tend to cancel each other out. When I'm at slightly low frequencies, right, I see the yellow curve is peaking after. That's, let's see, or current. Let me get down here far enough. Sorry, I'm trying to read upside down and backwards. All right, so in this case, what was yellow? Yellow is source voltage, and blue, this one is current. So right now what we're seeing, oh my gosh, I'm tired. We see current is peaking before the voltage when I'm at these low frequencies, right? So that's like ice. And then when I jack this frequency up even more, if I change the scale, so if I go to a slightly higher frequency, now it's switched. I see that the source voltage is peaking before the current. So this is exactly what we were expecting according to the graph up there. All right. Now, as I go to higher and higher frequencies in auto range, the current goes to 0 again. Now, in this case, I'm actually going to put these diodes back into here.
All right. And I think just to kind of remind ourselves of what we're trying to do here. Oops, let me go here. Here. Give me just a second. Hopefully I set this up the right way. So now what I'm going to do is try and go back to this phenomenological method that we used at the beginning. All right. So do we have a completed circuit here? Yes, we do. And so now, instead of using the scope, let's forget about the scope for a minute. Let's get all this out of here. I'll just make this simple. We've got our light, and the idea is when we go to really low frequencies, we don't see any lights blinking, right? As I go to higher and higher frequencies, we still don't see anything. But somewhere right around here, oh, where is it? Was it not plugged in? Oh, there it is. I don't know if you could see that. There's some spot where the lights grow brightest, and hopefully this is showing up. This is like, let me see if I can look at the screen. So there we go. At some point, you see the lights get really bright there. Okay, that is the special resonance frequency when the inductance and capacitance tend to cancel each other out. All right, so one last piece of conceptual knowledge, and then we'll take a break here. So what we see, if I go back to the board, is this. Now, what I'm about to draw is a different plot. Over here, we're talking about the voltage versus time. We see we can't draw a simple voltage versus time graph here because sometimes the capacitor dominates at low frequencies, and we see current was peaking before voltage. At high frequencies, we saw that the voltage was peaking before current because the inductor was dominating. In this case, we could actually make a plot. And is that going to hit? I'm running out of board. I got to go lower. Let me make sure that's showing up. That's pretty faint, but all right. I'm going to draw it again. I want this to actually show up. We see that as we change the frequency or change the angular frequency, omega, the current amplitude is changing. Right? Obviously, the current is constantly changing positive, negative, but the magnitude of the current at its peak. So the amplitude, or you could call this I max, the maximum amount of current changes. The light bulbs were getting brighter at one special frequency. We saw that when you hit the resonance frequency, there was a large amount of current. And when you're at really high or low frequencies, there was no current and no light. We clearly have some more work to do. So we'll do some math on this stuff in a minute. All right. So that's a brief introduction. It didn't feel brief, but yeah, that's a brief introduction to AC current terminology in terms of these phenomena like leading and lagging. We use the word in phase, right? Here, these things are not in phase, right? They're out of phase. One's leading or lagging. So in phase is when they're peaking at the same time, leading or lagging. We've discussed, we've talked about frequency period. We've talked about amplitude. We've talked about the source voltage as a function of time and kind of seen that working. Oh my goodness. All right. Hopefully that helps with some conceptual understanding. The next video will be